A very warm greeting, friends. So today this video prepared to present a presentation which will serve as a pocket guide for high shear wet granulation process scale up. We will discuss in this video all the strategies of process scale up for wet granulation, as well as we will arrive on the what is the best technique to implement. So friends, thank you for watching in advance, and be in the channel, like, share, subscribe the channel so that it will motivate us to make some more such videos. So let's start the video. So our goal of establishing scale-up rule is to ensure that the particle experience similar granulation condition across scales. So whatever the granulus characteristic we are getting in the lab scale, same we should get in the scale-up, pilot, and commercial scale. So generally, whatever the rules or scale-up rules are there, that can be broadly classified into two main categories. In the first category, it applies mathematical rules to process parameter based on engineering principles from one scale to other scale. So based on the engineering principle, we adjust our process parameter so as to get the same Gauss attributes. And the second way is by which we empirically adjust process parameter as needed to maintain the same Gauss attribute across scale. Means based on the observation, you adjust your process parameter. So in these two main categories, you can classify the scale up rules. So to achieve a best scalability, to achieve a best scale up parameters, dynamic, kinematic, and geometric, these three similarities required. So what are they? Let's discuss in the next slides. So before going to the scalar parameters, just briefly we discuss what are the wet granulation variables. So variables can be classified into two parts. First is the product variables, the second is the process variables. Variable means formulation variables. So the feed material, whatever the material we are using for granulation. So characteristic of the feed variables, like particle size distribution of the active substance and excipients, solubility in liquid binder, what it means that what is the water insoluble, what is the insoluble phase and what is the soluble phase. Then wettability characteristic of the material, packing properties, BD of the material, then how much fluid uptake you are taking, amount of liquid binder. So what is the binder, quantity of binder, viscosity of the binder, surface tension of the binder solution. So these are the product variables, so which we can fix in the formulation by excipient selection and formulation optimization, right? Whatever the process variables is impeller RPM, chopper RPM, occupancy, binder addition method, binder addition time, wet massing, or kneading time. So these are the process variables. So for scale up, we will focus on the process variables only. So the occupancy we can fix in the development itself, or based on the plant projections we can fix the occupancy, and occupancy we can keep the constant, right? Or we can establish by a range of the occupancy. So we will not there is no much scale up factors implemented in the occupancy. So occupancy to be fixed, binder addition method to be fixed, binder addition time we can fix. So basically our scale up rule will be applied on the impeller RPM, how to scale up the impeller RPM, how to scale up the chopper RPM, and how to scale up the kneading time. So these three things we will discuss in the next slides. So in the granulation, our endpoint, our main goal is to determine the endpoint and reproducibly arrive on that endpoint across the scale. This is our the main objective. So every granulation is different. In some granulation we'll do to densify the material so that it can be easily flowed on the machine, and batch processing can be feasible. And some granulation we want to control release of the drug release by the granulation. So based on that we will determine our endpoint. So sometime based on the mean particle size distribution, granule viscosity, and granule density. So based on that we will determine our endpoint. We will decide our endpoint of determination and determination. So our challenge is determining the endpoint, and then reproducibility of that endpoint with the change equipment size and models. So for that we will implement scale up factors. So let's go to the next slides. So gradation endpoint determination, there are various methods by which we can determine the endpoint. So like hand test, it is routinely used, earlier used a method. So by hand test you can determine your endpoint, but it is a inconsistent and subjective method. Some emerging methods are there: acoustic emission, image processing. Some offline method is there that by measuring the mass consistency, by particle size distribution evaluation. So these are the offline methods. Some inline instrumentation methods are there. By applying some pad tools, you can determine your endpoint. These pad tool function by measuring main impeller motor amperage, main impeller motor power, main impeller shaft torque. This is a figure. It is showing that when you start the addition of the binder, the torque and power increases, and then it become constant. So based on that you can determine your endpoint. Based on that you can determine your endpoint. So let's come on the our main target or main goal of this video, that across scale similarity. So across, to determine, to achieve across scale similarity, there are three ways, three important things which we know. First is the geometric similarity, second the kinematic, third is the dynamic. So if we figure out these three things, then we can achieve a proper scale up. So what is the geometric similarity? Same equipment design, uh, if the equipment is same and its h by d ratio, bowl height divided by diameter ratio is same, impeller design is same across the scale, then we say that all equipments are geometric similar. Again, if the design of the equipment design, if the h by d ratio, if the impeller design is same across the scale, then we will say it is a geometric similar. So the h by d ratio, mainly the h by d ratio of your lab scale and h by d ratio of your plant scale, if it is same, then they are the geometrically similar equipments, right? If they are geometrically similar equipment, then our scale up rule will be different. If they are not geometrically similar equipment, then our scale up approach will be different. Okay. Then we focus on the kinematic similarity. What is the kinematic similarity? The kinematic similarity refers to maintaining the same particle velocity inside the granulator. See, in small scale also impeller moves, and by that particle moves, and based on that we add some binder, and based on that some granulation and some nucleation starts happening, and based on that the size increase of the granules. So this is the basic mechanism of the granulation, right? So if we maintain the same particle velocity in across the scale, then we can achieve scale up. That is the principle of the kinematic similarity. Then dynamic similarity. Dynamic similarity refers to maintain similar forces or collision energy experienced by the granules inside the granulator. Some collision energy is experienced by the particles. So if we maintain the same collision energy across the scale, then we can achieve the scale up. We can achieve across scale similarity. That is the main principle of the dynamic similarity. So for a given equipment design in high shear wet granulation, the force experienced by the particle and the particle velocities are mostly dictated by the impeller speed. It is the main scale up thing, that impeller speed, it will determine the particle velocity as well as the force experienced by the particle, right? So significant effort has been put into establishing the best way to scale up impeller speed. So we will discuss in the next slides what are the different ways how we can scale up the impeller speed as well as other factors. So friends, we talked about the geometrical, kinematic and dynamic similarity. So these are the four different forces which a particle experience in a high shear wet granulation. First is the acceleration, which is mainly determined by the impeller RPM. Then frictional force in between the particles and in between the particles and particle to the machine, the frictional force. Then the centripetal force and the centrifugal acceleration, centrifugal force. So these four forces particle experience in the wet granulation. Similarity of these four forces across the scale will determine the our similarity of the granules across the scale. So friends, three scale up rules we will remember. First is the same constant impeller tip speed across scale. First is the constant impeller tip speed across scale. Second is the same constant Froude number across the scale. Constant Froude number across the scale. Third is the constant similar shear stress across the scale. So three rule now you remember. First, constant tip speed. Second, constant Froude number. Third, constant shear stress. So based on these three rules, we will see how to scale up the impeller RPM, how to scale up our granulation process, and which rule apply at which condition, that we'll discuss in the next slides. So now in this slide, first we remember three scale up rules. First is the constant tip speed, second is the constant Froude number, second is the constant Froude number, third is the similar shear stress. Okay, so how to implement these rules? Just remember one equation for all three rules. Just remember one equation: rpm 2, rpm 2, 2 means scale 2, means the plant scale. I will make it simplify. RPM 1, the scale you know, the scale you worked out. So it is a lab scale. RPM 2 is a plant scale, the scale for which you want to determine for which we want to scale up your product. So RPM 2 divided by RPM 1 equal to D1 diameter of the first scale divided by D2 diameter of the second scale to the power n. So this equation only you remember: RPM 2 divided by RPM 1 equal to D1 D2 power to the n. What is the n? For the first rule, means for maintaining constant impeller tip speed, the n equal to 1. Okay, n equal to 1 for maintaining constant impeller tip speed, n equal to zero point 0.5 for maintaining constant Froude number, n equal to zero point 0.8 for maintaining similar shear stress. Okay, so just remember this equation, forget all thing, and just remember the three scale up rules. So impeller tip speed, if your equipment are geometrically similar, it means same h by d ratio, if impeller design is similar, then you can easily go with the constant impeller tip speed rule. If your equipment is not geometrically similar, then you can go with the Froude number rule. So Froude number is essentially a ratio of the angular acceleration to the gravitational acceleration, and it is reported in the literature that for non geometrically similar equipment, because it is a constant value, so for non geometrically similar equipment you can go for a scale up with Froude number rules. Second, the third one is the shear stress. We seen that there are four forces which a particle experience during a high shear wet granulation. So the because of the frictional force, we can go with the constant similar shear stress rule, because we'll discuss what is the benefit of this also. So three rules but equation only one. So let's move to the next slides. So in the previous slide, we have seen that we can scale up the impeller RPM by three ways. First is by maintaining the constant tip speed. Second is by maintaining the constant Froude number, and third is by maintaining the shear stress. So we will practically also see, but first we remember the equation that RPM 2 divided by RPM 1 equal to D1 by D2 to the power n. By placing the n value, by changing the n value, you can change by changing the n value, you can change the rule, implementing rule, and by you can calculate the RPM2 by that equation. So we'll see practically now. Now just these three rules are there. So when you are implementing, see, by all the three rules, you are calculating impeller RPM at the higher scale. Okay. So when you are implementing the constant tip speed rule, then you have to change the kneading time at the higher scale. I'm again repeating that when you are going with the constant tip speed rule, then you have to change the kneading time at the higher scale. For other two rules like constant Froude number or constant shear stress, kneading time not to be changed. But when you are going with the constant tip speed rule, I mean n equal to 1 in the equation, then you have to change the kneading time. So how you can change the kneading time? This is just how you arrive on this equation. So T1 T2 equal to D1 D2, kneading time one at one scale divided by kneading time at the second scale equal to diameter of the first scale, diameter of the second scale, and n equal to 1. So this can be equal to the RPM2 RPM1, and this you arrive on this equation. So you remember RPM1 into T1, RPM2 into T2. This equation you remember to calculate the kneading time, means kneading time is inversely proportional to the RPM. So first scale RPM you know, because it is a lab scale. First scale kneading time you know, right? Second scale RPM you can calculate by the by our earlier equation, like this equation, because n was 1, so d1 d2 equal to, so RPM2 equal to d1 by d2 multiplied by RPM1. So by that you can calculate the RPM2 at the higher scale. Kneading time you can calculate here by dividing the RPM2 here. So T2 can be calculated by RPM1 into T1 divided by RPM2. So let's see practically how it can be done. So impeller RPM can be scaled up. I mean, impeller RPM at the scale up scale can be calculated by implementing three rule: constant tip speed, constant empirical shear stress, constant Froude number. Correct. So this constant tip speed rule will be applied when equipments are geometrically similar. What mean by geometrically similar? Means same H by D ratio. So and this is a table. So here impeller diameter at the lab scale provided, impeller diameter at the higher scale that is also provided. This is the impeller RPM at the lab scale, which is fixed by the development trials. Right now, we have to calculate the impeller speed at the higher scale as well. We have to understood what is the tip speed. Tip speed means with what speed the particles are moving inside the granulator. So that we have to calculate, and we have to understand all these three rule and how they implement. So let's move to the Excel sheet. So friends, this is the impeller diameter at the first scale 0.146. This is the impeller diameter at the first scale. This is the impeller diameter of the second scale, right? This is the impeller speed at the first scale. So if we want to apply the constant tip speed rule, then n value 1, right? So formula we remember, it is RPM2 divided by RPM1 equal to D1 D2 to the power n. So for the first rule, the n value will be 1. So we can calculate the RPM of the second scale by D1 by D2 multiplied by RPM of the first scale. I'm again repeating the formula. It is the RPM2 divided by RPM1 equal to D1 by D2. So D1 by D2 multiplied by RPM1 will give the second scale RPM. So what we did here, you can see B5. B5, what is the B5 is the first scale diameter divided by C5. C5 is the second scale diameter, correct, multiplied by the first scale RPM. So it will give the second scale RPM, that is 305.6. Okay, so for having the same tip speed as lab scale model, which is rotating at the 628 rpm, and impeller have 0.146, we have to rotate our scale up stage impeller, which having diameter of 0.3 meter, to at the rpm of 305.6. then we will get the same tip speed. Then for getting the constant empirical shear stress, n value will be the zero point 0.8. So applying the same formula, we can calculate the rpm, but here d1 by d2 to the raised to the power will become zero point 0.8. So you can calculate that value by this excel trick. You can calculate the formula power divided by b6 divided by c6. It means d1 by d2 comma n value, that is zero point 0.8 bracket close. So this will give you the value of the power d1 by d2 divided by n value it will give. Then multiply by the first scale rpm, that is d6. It will give the second scale rpm, which will come 353. Then a constant Froude number rule. So for the constant Froude number rule, n value will be the 0.45. So you can again calculate the scale up scale rpm by power b7 c7, means d1 d2 to the raised to the power 0.5, and multiply by the first scale rpm. So it will give the second our scale up scale rpm. So with the constant Froude number, our rpm will be 438.1. With the constant empirical shear state, our rpm will be 353. With the constant tip speed, our rpm will be 305.6. So which to be applied, that we will learn. First we will see three rules I told you. First is the constant tape speed, second is the constant empirical shear stress, third is the constant Froude number, correct. So let's see what is the happening by applying these three rules. So if you the tip speed formula is pi d rpm divided by 60. 60 divided by we divide by 60 because rpm is reported in the minutes, rotation per minutes. So by 60 we can convert it in the seconds. So tip speed always reported in the meter per second. So that's why this formula. So in the first scale, if you apply the formula, pi value 3.14, d value first scale d is the 0.146, rpm is the 628. So tip speed will come 4.8. Come, okay. So at first scale it will be same for the all three rules, right, because it is a development only. in the second scale, if we go by the constant tip speed rule, then our tip speed will be 4.8, calculated by the same formula by using the RPM 305.6. Okay. At the second, if we go with the constant empirical shear stress rule, then our RPM will be changed 353. So based on that, tip speed is calculated by applying the formula. So the tip speed is 5.54. So if we go with the constant Ford number rule, then our tip speed will be the 6.88. So you can see with the constant tip speed rule, tip speed at the higher scale is same, but by applying these three rules, tip speed is increased. So why these two rules are there? So it is noticed, we will see in the slide also, that if we go with the same tip speed, then particle experience more stress at the lower scale in comparison to the higher scale. At higher scale, if you keep the same tip speed, then particle experience less shear. So to because of that, you can may observe some scalar differences. So that's why these two rules are there. So they have a higher tip speed, correct? So they have higher tip speed, so that shear stress can be matched. So that's why these two rules are there. So as we discussed means previous slides also, if you have a geometrical similarity, go with the constant tip speed rule so as to maintain the same particle velocity, as well as you has to increase your kneading time. How to increase it, that also we will discuss, but you have to increase your kneading time so that you can achieve the same shear stress also. But if your equipments are not geometrically similar, then you can go with the Ford number rule. You can go with the Ford number rule. You can calculate the Ford number RPM of the second scale based on the Ford number, and kneading time you can keep same constant as the in the development stage. Okay. So then you can check the in development also, you can check the kneading impact on your product, and based on that also you can determine the kneading time, correct? So these three calculation are there. Whatever best suited for your product, we have to study during the scale up batches, we have to study. But the best way is, if your equipment are geometrically similar, then go with the constant tape speed rule, and increase the kneading time based, as we discussed earlier also, and we discuss in the next slide also. And if your equipment are not geometrically similar, go with the fraud number, keep the same kneading time, and imply RPM you can calculate by the constant fraud number. So let's see whether fraud number remains constant. This is the formula of the fraud number: n squared d by g. N is the impeller, n is the impeller diameter, d is the n is the RPM, d is the RPM the meter per second, and d is the diameter of the impeller, and g is the acceleration due to gravity. 9.8 value will be there. So this we calculated the fraud number for the lab scale. So lab scale RPM is 62.8. We divided by 60 to convert into the second. So n square 2 times, then d lab scale diameter, that is b7, and then divided by g value is 9.8 meter per second square. So fraud number comes 1.63. Same by that equation we calculated the RPM of the higher scale, it is 438.1. Same we implemented to check the fraud number, right? G7 divided by 60 into G7 divided by 60 multiplied by the C7 means higher scale diameter divided by acceleration due to gravity. So here fraud number is 1.63. So both fraud numbers are same. So by the constant fraud number, so we will get the same fraud number. So again I will summarize that just this two things I tell you just to check whether what is the tip speed and what is the fraud number, right? You have to remember only one equation, that RPM2 divided by RPM1 equal to d1 by d2, diameter of first impeller, diameter of the second scale impeller, raised to the power n. N will be 1 when constant tip speed rule will be apply, n equal to 0.5 when fraud number will be applied, n equal to 0.8 when empirical shear stress rule will be applied. So before going to the slide for the kneading time calculation, just I want to show this slide. So if you see this slide, in this slide for the different scale, for example, the this scale 65 liter and 150 liter, the tip speed are nearly same, correct? For this scale 300 800 liter, the tip speed are nearly same. Here also nearly same tip speed, but when you see the centrifugal acceleration, so it is it is different. At 65 it is higher, at higher scale it is decreasing. So as we are moving to the higher scale, by maintaining the constant tip speed, the acceleration decrease. So because of that, what happened at higher scale, if you are going with the only tip speed, then particle experience less shear. So when you are going with the same tip speed, which is the best way, so then you have to increase your kneading time so that you can compensate this centrifugal acceleration. So the data on the centrifugal acceleration reveals that one might expect high compaction force in smaller machine at the same level of the tip speed. So we can calculate the kneading time, we can adjust our kneading time based on our scale up observation as well based on our product characteristic. So let's see how to calculate that. So in previous slide also we arrived on this equation that rpm1 into t1 means kneading time at the first scale is equal to rpm2 into the t2. So if we are going with the constant tip speed rule, what it means, if we are calculating the RPM of the second scale by keeping the n value 1, correct? So then we have to increase the kneading time and we can calculate the kneading time by this equation. RPM 1 T1 which we fix by the development study, then RPM 2 which we calculate by the our equation, and kneading time at the second scale can be calculated by dividing the RPM 1 into T1 divided by RPM 2. So that kneading time we can implement for our scale up. Let's move to the Excel sheet to see this calculation. So this is the equation rpm1 into t1 equal to rpm2 into t2. These are the speeds at the different scale which we calculated by the constant impeller tip speed rules. So at the first scale the wet masking time is the 30 second. So at the lab scale of the 10 liter we can calculate the second wet masking time by d26. So d26 is the rpm at the first scale, means rpm 1 t1 means 30 second, then divided by the second scale and 305.6 rpm. So rpm 1 into t1 divided by rpm 2. So at 10 liter our kneading time will become 62 second. Same at the 65 liter our kneading time will become 103, calculated by the applying the same principle, correct? D26 into E26 divided by D28. This value we calculated by the same tip speed rule, means the formula rpm2 divided by rpm1 equal to d1 d2 rpm2 equal to d1 d2 multiplied by rpm1. So by this method we can calculate our kneading time. So finally, the conclusion. So based on our discussion, for the equipments which are not geometrically similar, we can go with the fraud number rules. If the equipment are the geometrically similar, means same H by D ratio, same impeller design. So best rule is we can go with the constant impeller tip speed rule, and we can calculate our impeller RPM, our chopper RPM based on the constant tip speed rule. For chopper also same rule will be implement. So we can go with the constant impeller tip speed rule, as well as we will the wet masking time, the kneading time, we can calculate as we discussed in the previous slides. The binder quantity, it will scale linearly. No need to change the binder quantity. If you are taking the 20% fluid uptake in the development, then same uptake you can go with the plant scale, while reducing the impeller RPM based on the impeller tip speed calculation, and increasing the kneading time based on the RPM, RPM1 equal to TT1 equal to RPM2 into T2 by that equation. So this is all about the scale up of the wet granulation process.